one shown here. I had a picture of Dr. Genero out in the field collecting samples in a stream. They're looking for PFAS concentrations underneath the stream and in the stream water. And what they've determined is that rather than PFAS flowing from the stream into the groundwater, it's the other way around. The groundwater is a continuing source of contamination of the river. And they've determined that PFAS is flushing out from the groundwater through little creeks that run into the Cape Fear River at a rate of about 60 nanograms per day. So the next step his team is going to take is to use that information to figure out, well, how long is it really going to take for all those PFAS to flush out of the groundwater that were, originally originated from the Chemours facility. They've also determined that about 2 nanograms per liter of Gen X and about 8 nanograms per liter of total PFAS in the Cape Fear River likely are originating from groundwater. That's, again, the groundwater is flowing into the little creeks. The creeks flow into the river. And so that's their finding. So anyway, the main highlights from my part, though, is that Gen X in private wells seems to be coming from the air. That's, again, our work so far is confirming that hypothesis. And even with only a little bit of data, so far we can build a pretty good predictive model. And I expect it to improve a lot once we can get information on the characteristics of the wells. So our next steps, collect data on well characteristics, refine the model, make it publicly available, answer the question of how long it's going to take for all that stuff to flush out of the water. And with that, I want to really acknowledge the North Carolina Policy Collaboratory for bringing us all together, especially the incredible effort of Jeff Warren to get this thing going, and introduce all of these researchers from all these universities to each other. Some of us were working together already, but he really built a much bigger and stronger network. I wanted to also acknowledge my collaborators on this work. I am not a chemist who really understands how contaminants travel through the subsurface. And then Zenora Sailua at UNC is helping us to track down well permits. She's calling health departments, and our next step is to survey and or call owners of the wells that have already been sampled to see if we can get that information. And then Riley Mulhern, a PhD student in my group who's also been contributing to this effort. And we have a few minutes. Looks like we have 5 minutes for questions. Okay.
We have about 5 minutes. So as we're looking at these questions, 2 things. Please, if you would, when you send in your cards, write the researcher's name on them, because some of them could apply to different researchers. So please put their names on there. And also, a number of these are very interactive type questions. So we, again, invite you all to join us at the reception where you have a fair amount of time, about an hour and a half of commitment from these researchers to talk to them one-on-one. So we have time for about 3 questions. The first is, can your model do this prediction for wells around other facilities such as military bases or other industrial factories?
Yes, I mean, I'd love to try to validate it at another location. We'd probably want to take the structure that we have and take observations from those kinds of areas to kind of relearn the parameters of the model. But that would be a really interesting, I mean, that's kind of the whole goal, is to figure out whether this can work for other areas as well.
Okay, second question. How far away from the Fayetteville Works plant are you finding contamination in air? And I know we'll hear about this.
So that is something that I guess the air group will probably be answering. So shall I defer that for them?
If you'd like to.
Yeah.
Sure. Third question, with the variable distributions or patterns of contaminant levels around Chemours, is it related to the depth of the water source, or the real question is the contaminant level uniform or not, and to what depths do the contaminations reach?
That's a great question, and that's one I hope we can answer once we're able to get the information about how deep the wells are. So again, what we're predicting so far is really only based on the surrounding location of the well relative to the wind direction, its distance, the type of soil, impervious surfaces, other potential sources, those kinds of things. We don't have the well depth information. I expect that that will become very important, and that we'll get much better trade-off between false positives and false negatives once we have that information. I would expect the shallower wells to be at increased risk. That's a little bit represented by that elevation variable where the wells that are at lower elevations, well, they may not, they may be shallower wells, or they're just in the direction of downhill flow from sources.
Okay, thank you. Last question that we have time for right now. Is North Carolina, in relation to the PFAS crisis, coordinating with what EPA is doing, and this is specific to your work, and or the Center for Disease Control?
Boy, that's one I can't answer. I think the policy collaboratory staff may know more about that than I do. I'm the number cruncher on this project.
Okay. All right, we thank you, Dr. McDonald-Gibson. Okay, well, I don't need to step up there. So, Team 3 is the PFAS Removal Performance Testing Team. Dr. Heather Stapleton with Duke University will be the speaker representing her team today. Dr. Stapleton is an associate professor of environmental chemistry and exposure science at Duke University. Her research focuses on identifying chemical additives in consumer products and measuring contaminant personal exposures in the general population. The PFAS Removal Performance Testing Team, the goals are to identify optimum strategies for removing both legacy and emerging PFASs from contaminated surface and groundwater in North Carolina as well as from finished drinking water.
Good afternoon, everyone. Thank you for the nice introduction. So it's my pleasure to be here today and represent Team 3. I just wanted to start out by acknowledging all the members of this team. This is truly an interdisciplinary team of researchers focusing on this question of how best to remove PFASs from different water sources and waste streams. As you can see here, we have 5 different researchers from actually 4 different universities working on this project. Professor Cornell from UNC Chapel Hill, Professor May Sun from UC Charlotte, Professor Detlef Canopy, who you've already heard from in Team 1, is also part of Team 3, Dr. Frank Lightbirth from Chapel Hill, and myself from Duke University. All of us have different expertise we bring to this project in terms of understanding how we can best remove PFASs. So you've heard a lot about this. You've seen many similar slides. I'm not going to go into a lot of details here, right? But really, the problem here that Team 3 is really trying to address is how do we remove PFASs from various water sources and waste streams, right? We know that these compounds are very stable. They're designed to be very stable. And carbon-fluorine is actually one of the strongest bonds. It is the strongest bond there is in any of these chemicals, right? So they end up from the products, manufacturing facilities, in our surface waters, in our groundwaters. And for many of us, our water comes through some type of treatment process. So here I'm just representing kind of a general schematic of a surface water source up here that might end up going through wastewater treatment. And even though drinking water treatment facilities are designed to have multiple capabilities to remove various types of chemicals, unfortunately, the structure of PFAS molecules allows it often to go through these processes, no matter what's present. And you can see here, this is representing Gen X, can potentially go through all of these and end up in the drinking water pipes that come to your home and then out into your tap. So we have 2 questions we're really trying, or 2 areas we're addressing here is how can we best make recommendations or understand research to help us improve removal technologies here for drinking water treatments, and also understand really how these filters, the point of use filters that we might have in our home, how well do they remove PFAS molecules. So some of the specific questions that we're trying to address are what's the best option to remove them from the drinking water? For these commercially available membranes, ion exchange, these various resins that are often employed in drinking water utilities, what are the best choices and decisions to make for including these? Can they be optimized, et cetera? How do we remove them from certain waste streams? Are there novel, new methods, materials that we can develop to help remove these? And as I said, how efficient are some of these point-of-use filters in our homes for removing these compounds? So what I'm going to do is each one of these team members has provided me a couple slides from the various ongoing work in their laboratories, and I'm going to do my best to describe that to you here, and some of the preliminary results and where they hope to go with this data. So I want to first talk about some research in Dr. Cornell's lab at UNC Chapel Hill. He's really interested in evaluating the various types of membranes, these thin sheets or different materials that can act as almost physical barriers for removing some of these from the waste streams. So he's interested in understanding how different PFAS molecules, based on their physical chemical structure, their size, different functional groups can be removed with different membranes, how different membranes work, and whether you can make slight modifications to the surfaces of these membranes to help remove some of these chemicals. Right, so currently he's looking at 29 different types of PFASs. You saw earlier there's actually thousands of different PFASs out there, but generally we're focusing on several dozen that we know where there's some health concerns and are more prevalent, particularly in North Carolina. They all have very different sizes, polarity, physical attributes that will affect how well retained or removed they are. So it's important to look at multiple PFAS molecules. He's looking at 10 different types of high-pressure membranes. Some of those I think they're working on in-house, and some of those are just commercially available. And then characterizing this based on different water sources, groundwater, surface water, deionized water, because it's not just PFASs in the water. There are other chemicals as well, dissolved organic carbon, other contaminants, metals. Those can all affect that ability of these molecules to be retained by these filters and these membranes. So this is a slide that Dr. Cornell provided me with, kind of just suggesting or demonstrating some of his preliminary results. So these are 3 different membranes. The membranes here are on the x-axis. I know these little acronyms are going to not be important to you. The CE represents a brackish water commercial membrane. SWC4 is a saltwater commercial membrane. And the one in the middle here is a nanocomposite membrane that his group was developing in-house. And so then you can see on the y-axis, it's the percent removal of these 3 various perfluoral PFAS molecules. Again, focusing on ones that are more prevalent or more of concern, particularly in North Carolina. So PFOA, that C8 molecule. PFBA is like PFOA, it's just smaller, it has 4 carbons. And then Gen X, which is actually kind of intermediate in length at least. And you can see here the brackish water membrane, commercial membrane, removed a good portion, but not 100% and not nearly as much as what they saw in the nanocomposite membrane, and actually this saltwater membrane here, which seemed to remove more than 99%. But again, that's just for these 3 chemicals. So there's ongoing research to understand how well these membranes can actually remove other types of PFASs that'll have different properties. Okay, and so this is a slide from Dr. Detlef Canopy's group and his PhD student, Zach Hopkins. They're also evaluating the different characteristics of activated carbon in terms of how well they can remove some of these PFAS molecules. So what they're doing is collecting water, and I believe this slide represents water from the Cape Fear River, and how well it's being removed by different volumes of water and granular activated carbon. These represents the volumes of these, and so understanding how this relates to that potential for these chemicals to break through the carbon, which is what you're looking at on the y-axis here, right? And then for the various different types of PFAS molecules. You've seen some of these acronyms, some of these might be new, but these are all different types of PFAS molecules, with the exception, obviously, of TOC, and that represents total organic carbon, right? So down here you can see how much is retained based on the bed volumes in these experiments. Certainly what you're looking for is a low number here, because you don't want it breaking through your filter into the effluent. So this represents a ratio of the concentrations going into the filter and what comes out of this, the activated carbon. So you can see here, you get almost all of it being retained, not breaking through the filter, but over time, and you can actually get some coming through. And then occasionally you can see that some of these are going over 100%. And that's unfortunately because there's other things in the water. And when they come in and you get some of the saturation on these carbon molecules, they can displace some of these PFAS molecules, and it'll be released. And you can end up with more in the effluent coming out than what came in originally. And I'm going to talk about some of the point-of-use filters in homes that we've been sampling. We've actually seen the same thing occurring. All right, so Dr. Frank Lightbirth is actually trying to develop new membranes and new approaches to removing perfluorochemicals. One of which he's working on are these ionic floral gels. So this is trying to create new polymers or new sorbents to retain these materials. And so he's trying to use both this approach where it combines these floral gels, so it's a polymer with fluorine on it. Let you remember this term, likes dissolves likes. So by having the fluorine in there, it helps to bind some of these PFAS chemicals. And then he adds this ionic component to it as well, because part of the PFAS molecules are often charged. So this should enhance the ability of these materials to retain and absorb the PFAS molecules. And so here's some of the preliminary data from his laboratory. And what you're seeing here on the bottom are these different materials he's been testing. The one on the left here is just an ionic gel, so that charged material, just a fluorous gel, so just containing the fluorine. But when he combines them, you can see that these bars are much higher, this suggesting how much is actually removed. So he gets a much higher proportion, close to 80% removal, again, of these three. He's focusing on these three. There are slightly different PFASs than what Dr. Cornell was focusing on, but it does include PFOA, Gen X, and here is the hexanoic acid, so it's the C6 molecule. But you can see by combining these technologies, he's actually able to remove more than these two if they were just used on their own. Right, so he's really trying to understand the conditions by which you can optimize these to actually improve removal of the PFAS molecules. All right, and then Dr. May's son at UNC Charlotte is really interested also in electrochemical mineralization of the PFAS. How can we actually degrade these molecules, right? So you've heard this term forever chemicals. They're very persistent because of those carbon-fluorine bonds. It's not possible to break those bonds by sunlight, by bacteria, UV light. You know, these are all approaches we use to kind of remove or break down chemicals. It doesn't work with PFAS, unfortunately. So what we're trying to develop are these new methods that involve basically like electricity. You know, you're just forming these energy sources that can deliver these high powerful electrons that can break those carbon-fluorine bonds. Right, because this is the ultimate goal, is you want to degrade them, and degrade them to things that are not toxic, right, and that's also important as well. So her lab is working on these different materials to explore electrochemical mineralization, so this ruthenium oxide titanium material, another type of ceramic material, and then this graphene membrane material as well. And so she's here provided some results from some of the experiments in her lab, so you can see the setup here. You can almost think of it as kind of like a battery setup. And in this experiment here, she found that when she had a certain concentration of PFOA in the system, and in this case she's looking at the titanium ruthenite oxide electrode, she had 93% removal of the PFOA. So a lot of it disappeared, right, but she's still trying to identify what those breakdown materials are, what they look like. Is it completely breaking down to fluoride and CO2, or to short-chain PFOAs? And that's some ongoing work that is also very important within the scope of this research. And then she'll also be testing some other conditions and also obviously looking at other perfluorinated compounds. All right, in addition to looking at those opportunities to degrade PFAS through electrochemical mineralization, she's also interested in conducting more research on understanding how certain materials like ion exchange and some other membranes can also remove these perfluorinated chemicals. So as part of her plan, she hopes to look at the various different materials within ion exchange. And I know I won't get into a lot of details of all these different chemical properties and functional groups, but this schematic over here represents what you might think about as that resin that could be in a filter. And as your water comes through it with these perfluorinated chemicals, it has lots of different properties. So there's kind of a polymer backbone, which is represented by the black lines. And then you can get these different functional groups that have different charged components to it. Right, because a PFAS molecule has a very hydrophobic end. It's very sticky. It likes to stick to things. And then you got this polar part that makes it really soluble. So by combining features that can absorb both of those properties, it helps again to retain these molecules. And so they're trying to explore a variety, using different varieties of these approaches to remove these compounds. Right, so her plan is to test several different ion exchange resins through different commercial suppliers and categories, as you can see over here. Test them on groundwater from Fayetteville, right, and surface waters from Wilmington, and explore not only how much can be degraded, but as I said, what are they degrading to, so we understand what those degradation products are, how fast is it degraded, how much is absorbed at different temperatures, and then understanding kind of the mass balance of the approach. And then what's required to remove those PFASs for a waste stream and regenerate it if necessary, regenerate the ion exchange capacity. Right, and so this is some preliminary results from my lab. So I've been working with Detlef to kind of examine how well filters in our home remove PFAS chemicals. So I know Detlef has been working with the community here in Wilmington. He talked a little bit about the high concentrations of PFAS in the Haw River. The Haw River is a source of drinking water to the city of Pittsboro. So my group at Duke University has been working with the city of Pittsboro, residents in Pittsboro, and actually in Cary, Apex, and Durham as well. The Haw River empties into Jordan Lake, and we know that there's PFASs in Jordan Lake. Jordan Lake is a source of water to the cities of Cary and Apex. And it looks like, based on the data so far, that the contamination of Jordan Lake is a result of everything in the Haw River coming downstream into that. So then there's concerns about levels in the water systems is there as well. So that's why we're working in both areas to really understand how well these filters in our home remove it until we can find solutions for these water utilities. So what we did is we contacted interested participants and residents in both areas. We had a team that went to the home. We collected a liter of water from the tap, what came out of your faucet, and then we collected a liter of water that went through whatever filter that person had in their home. Some people use a pitcher filter, like a Brita, that has these cartridges that usually contain activated carbon. Some individuals have a refrigerator filter. You go up, there is a filter behind that door. That's usually a cartridge also with activated carbon. And then some homes have these more advanced reverse osmosis units. This is a picture of one that's under the sink. Sometimes there's whole house filters. There are other type of filters that are whole house as well that have ion exchange. So we've sampled about 70 different homes at this point and trying to understand how these different filters work in your home under conditions in which we use them to remove these chemicals. So this table shows you our data to date for several different perfluorocompounds. So here's Gen X at the top. And then we have several other perfluorocompounds. This is not the only list of chemicals we've looked at. There's actually 12 of them that we're evaluating in terms of their removal efficiency, where you go from the smallest C4 to C8 here. And you can see how the different filters work. As already indicated earlier, I know Dr. Canopy said this, the reverse osmosis seems to work best. We see basically 100% removal of all the PFAS chemicals we look at. As I indicated before, some other chemicals might go through, but for the PFASs we've measured, we see 100% removal. However, most of the filters that have activated carbon, in particular the pitcher filters and the refrigerator filters, they do retain some on average, but you do get breakthrough. So these numbers here represent the percent removed, and they're an average. And I will say, particularly in the refrigerator filters, we've seen quite a range of how much is removed. We actually had an extensive survey of how old the system was, the filter was, how often do they change the cartridges. You're surprised. Some people's like, oh, I haven't changed that since I moved into the house. And other people change it quite regularly. But unfortunately, it was not related to how well that filter worked in terms of removing those PFAS molecules, which was actually surprising to us. And we believe this is due to several things. Particularly in refrigerator filters, you can't see that cartridge, but they probably vary from manufacturer to manufacturer in terms of how much carbon is actually in that cartridge or whether there's other resins in there as well. Also probably depends on what else is in your water, right? Because you can get saturation on some of these sites. There's a maximum amount of material these filters can actually absorb and remove before they become saturated and things go right through. Or as we saw before, sometimes you can actually get release of things from these carbon filters, and then they come out and you have higher concentrations in your filtered water than you do in terms of the tap or the raw water. So it's quite a range that we saw in the refrigerator filters, and so really still trying to understand these different attributes of the refrigerator filters in particular in terms of how well they're working. Some worked very well, some didn't work at all. But on average, you can also see that when you look for the C4 to C8s within this class of PFAS, that with increasing size of the molecule, you get increased efficiency of removal, right? So the bigger ones are removed better than the smaller ones, and that's been seen in other areas as well. So this is something we're continuing to work on in our laboratory, and we actually have a poster on this that we'll present later too if there are additional questions. So in terms of expected time, that's kind of a brief overview of all the different projects I recognize, and certainly you can reach out to anyone that many of my colleagues or team members are not here, I know with the exception of Dr. Canopy. I'm happy to answer questions, but we're hoping that we'll have a majority of this research completed by early 2020. The goal is certainly to generate reports and manuscripts, but really, the overarching goal is to kind of provide recommendations on the different types of filters that could be potentially incorporated into commercial scale drinking water utilities, and maybe even help inform design of point of use water filters in the home as well. And certainly hoping to connect or communicate these findings to other stakeholders as well in 2020 when the research is complete. So I'll stop there. I certainly want to acknowledge as well the NC Collaboratory and everyone for helping to support this work. Thank you for your attention, and if there's time for questions, I'll certainly be happy to take them.
There are. Thank you. Am I the only one wondering when the last time I changed the filter on my refrigerator is? Okay, question number 1. Good question. What should be done with the backwash water from the filters that now contain the PFAS compounds? Boom.
I know. That's a very good question. I know it's something that comes up a lot. I think this is why there's a lot of interest in understanding what these techniques, particularly this ability to mineralize some of these compounds, electrochemical degradation approaches to remove them. But right now, particularly if you have an RO system, you have that permeate stream, which is where all those PFASs are then concentrated, and they're going down to the wastewater, down through your pipes back into a wastewater treatment plant, and you kind of get this circulatory effect. It can come back. That is a problem. So it's something we need to think about, and I don't think we have a solution yet.
Okay, second question. Will you or your teams be able to estimate the cost associated with the different technologies you're evaluating?
I don't think that's within the scope of our research plans, and a lot of it's because what we do in the laboratory can be very different when you scale it up, particularly to a drinking water utility, and so there's other costs and things that go into that. I'm sure there may be discussions about that, but I know it's not our initial plan to estimate costs for these things, is my knowledge.
Right. Okay. What level of contamination remains in the water mains and the connectors of various types to the tap?
Remains in the I'm not sure I'm following the question.
I suppose what they're saying is, do we have contamination that runs through the piping systems and the various plumbing, I suppose, that run to the tap?
So I guess I'm assuming the question means, so after it's treated at a water utility, as it's transported to the home through these pipes, is there any contamination coming from those pipes? Again, that's not something we're actually evaluating in Team 3, and I'm not sure if any of the other groups are evaluating that either. Detlef, I'm getting some no's here, I'm not sure. I mean, those materials should not be a source of PFAS. Most of them are PVC pipes, so.
Do you want?
We looked at it a little bit here in Wilmington, where we compared the levels at the treatment plant entering the distribution system and then at people's homes. And the distributional concentrations we saw was very similar. So
Right.
I would say there's really no change.
Right. I know we've done a lot of sampling on the Haw River, as similar to Detlef, and what we see in the Haw River looks identical to what we've seen in the tap water for the people of the city of Pittsburgh as well. So it looks identical and the same. It's not like it's higher or much lower. It looks very similar.
Okay, I'm not sure you can answer this, but I'll ask it. Are you able to, which of the RO systems do you suggest or can you suggest to residents, if you can? And do you think that the GAC systems alone will work for water companies?
I might let Detlef answer the GAC question. I mean, there's lots of RO systems out there, and I can say within our study we evaluated 12 different ones. All of them work to remove the PFAS as we measured. Again, keep in mind there are other things that may not be removed by RO systems. So, I mean, I think most of them that are on the market are good. The thing to keep in mind is that these RO systems are a lot more expensive than buying a pitcher and things. So that just brings up, I think, even environmental justice kind of questions when you want to remove these. So that's something you have to keep in mind. I actually put one in my home in Cary, because as I said, Lake Jordan's a source of my own drinking water, and I was kind of surprised to see them in there. And it turns out they're coming from the Haw River. The one I put in my home was around $350. It was just an under-the-sink one, so they're kind of pricey, and you still have to replace the cartridges every year. Those cartridges cost almost $100 as well. So it's pricey, and you have to realize that. I think having any filter is helpful, but if you do have the activated carbon, change those filter cartridges out as recommended. That's really important. I mean, it's something. Yeah, do you want to?
So one question was related to GAC, and is GAC alone a good option, or will it work for water companies? And so based on the data that we've collected so far, the answer is yes, as long as you change the carbon out sufficiently often. So for a while, GAC removes all of the compounds to below detection, but at some point they start breaking through, and the shorter chain compounds break through sooner, the longer chain compounds break through later. So it becomes an operational decision and a cost decision. What do you use as a criterion to change out the GAC? And so that's where I think the interest of the community probably is, will the utility remove all PFAS, or will it will it run the GAC until some PFAS break through? So that's up to the operational criteria for the water treatment plant. But GAC does have the ability to remove all the PFAS that we've seen in the river to below detection for some time. So the other question is, are reverse osmosis membranes a good option for wells? And I assume this goes for private wells, and then I guess the question would be, are you thinking only about an under-the-sink system to treat the water that you drink? If that's the case, then I would say, RO membranes would be effective for removing PFAS from the tap water that you drink and use for cooking. But RO filters would not be a good option for whole house filtration at a private well, because you would waste too much water, you would generate so much concentrate that it may even overload your septic system.
All right, thank you again to both of you for answering those questions. Okay, thank you all for hanging in there with us. We have two more teams. Team 4 are the Air Emissions and Atmospheric Deposition team. Speaking today for the team is Dr. Ralph Mead from UNC Wilmington. Dr. Mead is a professor of chemistry and biochemistry at UNC Wilmington. He is an organic geochemist focused on developing and applying molecular and isotopic analytical techniques to trace naturally derived organic carbon in the marine environment. And the overall focus of Team 4 is to better understand the airborne composition, distribution, and concentrations of gas and particle phase PFAS. Thank you, Dr. Mead.
All right, well, good afternoon, y'all. It is a pleasure to have a chance to come up here and to represent Team 4 and all the great work that we have here. And as Tracy said, my name is Ralph Mead, and before I move on, I would like to go ahead and introduce the rest of the team. So myself, of course, and then Barbara Turpin, our co-leads, along with the rest of the investigators, who are May Sun, Bob Keeber, Brooks Avery, Steve Scrable, Joan Willie, Jason Surratt, Karsten Bowman, Wanda Bodnar, and Zinfei Zhang. Before I move on to the next slide, I have to acknowledge the work and efforts that our postdocs do, as well as the graduate students and undergrads that are in the laboratory. Without those folks, Team 4 would not be where we're at now. All right, so before I start into this, I just wanted to give you guys a little bit of a background as to the motivation of why we propose this work, why it is important. So first off, there is currently a paucity of knowledge regarding the concentration of PFAS in both wet, dry deposition as well as in aerosols. We know that the legacy compounds such as the PFAS, they have a global distribution and are found in areas of the globe that they really should not be there other than by atmospheric transport. So does the same thing apply for the replacement compounds like Gen X? Another motivating factor, of course, is the human side. That is, what are we exposed to in the air through what we inhale, as well as an indirect exposure to, say, river waters that have had atmospheric deposition, and of course we pull our drinking water from. Sources. What are the sources to the atmosphere for these PFAS compounds? It can be broken up into a point source as well as a non-point source. That is, a non-point source would be a good example of the things that we use in our everyday life. In blue here is one of the key points that we still are not entirely sure as to what sort of atmospheric transformations these PFAS compounds undergo once they are released. It's important because without having that information, it makes it tough to help predict what sort of impact that atmospheric deposition will have to, say, a drinking water source. Another motivating factor here is this idea of elevated concentrations of PFAS within the indoor air, and especially near an urban and industrialized sources. So in the box here, we have basically a key point here of Team 4, fate and effects of atmospheric-derived PFAS are poorly understood. We hypothesize that a lot of this is going to depend on the chemistry of these compounds and their properties, such as chain length, things like that. All right. So with that, then, I would like to go ahead and describe the key questions that our team has. And the top, way up there, can be basically broken down into an overarching question of what PFAS compounds are present in ambient air, as well as wet, dry deposition. From that, you can build the rest of the questions. What is the geographic distribution, and what does this tell us about the source of that PFAS? From there, what is the contribution of wet, dry deposition to the Cape Fear River Basin on an aerial extent? And last but not least, How does the gas to particle conversion, that is the multi-phase chemistry during air mass transfer and transport alter the fate of PFAS? Over on your right-hand side here is a variation of a cartoon which y'all have seen now for quite a few talks here. The key thing I want you to take from this is this top part, the atmospheric part. If you have a point source, say, that is directly emitting PFAS, there are a variety of atmospheric transformations that could take place, such that you can have conversion of the initial compound into something else, such as shown here, as well as, depending on where that air mass is from, that is where the wind blows, that PFAS can be transported both a short way as well as long-range transport as well, where ultimately, whether short range or long range transport, PFAS can be deposited, both say wet, dry, deposition, or exist as an aerosol for multi-phase chemistry to take place. All right, so our planned approach is basically, it is tough to predict when it is going to rain, right? And especially right now in our drought. But with that, we have a very unique rain site here, a wet precipitation site that has been continuously used for atmospheric research for 20 plus years. And we're going to use that to sample event-based wet, dry, deposition. The importance of the event-based is we know when the rain began, we know when the rain quit. That's important because then from there we can relate that back to where that air mass came from. Based upon that, or adding to that, we are also have a integrated aerosol that is gas and particle sampling throughout the state, where we weekly for 6 days over one year throughout the state. What this will do for us then is basically tell us a high temporal and large spatial extent of gas and particle PFAS throughout the state. We'll also have real-time measurements of highly polar PFAS of a very short time frame because of the type of instrumentation that is required to do that work, but the results that we get from that are one of a kind. From there on number 4 here, we will combine a low resolution MS and a high resolution MS approach to quantify as well as structure elucidation of the PFAS that we detect in our air and wet, dry deposition. From there, we will take these results and build a model and predict, based upon the measurements which we have obtained an aerial deposition to the Cape Fear itself, and from there as well to help interpret the distribution of PFAS which we find. We will use a variety in item 6 here of ancillary information to help predict and understand where that air mass came from and how that impacts the PFAS concentration as well as distributions. And lastly, we'll have a very intensive benchtop laboratory experiments with one of the building blocks of these replacement PFAS compounds. This part of the work is really a unique aspect of Team 4, and we are very excited to see how these results come out. All right. So on our screen here, we have a map, of course, of our state, and what I want to point out here is each of those pin drops are a sampling site that we are going to do wet-dry deposition as well as aerosols. That's the case for most of the sites except for Bald Head and App State, way in upper left-hand part here. Doing this type of work requires a site that one can be manned, someone there to take care of the instrumentation we have, as well as a power supply. So this is, it might not seem like a lot of points, but the logistics that go into this is quite tough. All right, so here we have an example of our aerosol or gas and particle phase site at the Honeywell sampling site in Fayetteville. Our colleagues at DAQ were kind enough to share the facility with us, and you can see in your upper left hand, this is the area, and these series of images highlight how the air is pulled through, and within the canisters here are a variety of absorbents that will trap the gas phase as well as particulates. All right, and here we have a little bit closer to home. This is an image of our wet and dry deposition site here on campus. This is a combined site where we have, like I said, both wet-dry deposition as well as gas and particle phase collection. Over here in your left-hand side are wet-dry deposition collectors. Since the sun is out, where that top little tray is covering it's covering the wet deposition pail. When it starts to rain, the lid will move to cover up the other pail, and now the pail that is exposed will trap any of the wet depth that falls down. And as you can see here is the image of the same air and particle phase collector, which I showed on the previous slide. All right, so this is a slide, and it is similar to the slides you have seen before, the sample workup, and it basically starts off with in the field, both whether it's wet, dry dep or an aerosol. There is an extraction pre-concentration that takes place, and the samples are analyzed on a high-resolution MS, and then, of course, on a low-resolution as well. Having both of these type of analyses will allow us to quantify as well as do some structure elucidation as well. All right, our sampling timeline. So the map up in the upper left is the map you've seen before, and what I have shown here is basically, this is an old slide, basically shown here is the breakdown of the quarters, and where you see an X is the duration of sampling. We will collect wet-dry deposition continuously throughout the whole year here at our site. Like I said, because we're here, we have students who are more than happy to go out and collect as soon as it ends. And then, of course, there's the dry deposit, or at our other sites throughout the state, we have 3 sampling events for the winter, as well as a summer campaign. And again, these are remote sites, and we're relying on folks to come out there and do the collection for us. As well as the gas particle phase collection is throughout the whole year, and then a very intensive summer campaign of real-time, high-resolution MS data for gas phase PFAS, which will start in the summer here. All right, what can we use with the information which we obtain? Here we have an example slide here of 2 rain events that were collected here at the university at our wet-dry deposition site. And the dates are up here, so we'll start with the one on your left first. So this was a rain event where E is event, and then the 1775 is just the number of precipitation event. And the concentration in that, or actually the volume of rain was about 1/4 of an inch, and the Gen X that we measured was, of course, below our limit of detection. You say, okay, that's fine. Well, the interesting thing about this is you can hindcast, that is, go back in time and model where that air mass came from. So, I don't know if you can see it or not, but the star, where my green little pointer is us right here. We can go backwards in time 24 hours and show that air mass came from purely off of the Atlantic. So you could consider this as a marine sourced air mass. Okay, you say, okay, that's fine. Now compare that to this one, to this rain event, which was about a week and change past, and you see that the Gen X concentration here was off our highest point on our calibration curve. And the rain event, the total amount of rain we received was about 1.8 inches here. And again, doing the same 24-hour hindcast plot where we are the star here, you see that air mass came from over the land. All right, so it picked up, as that air mass moved across the land, it picked up this Gen X along the way. Okay. Our outcomes, what is it we hope to have when we're all said and done here? So the proposed research will provide critical and transformative information regarding the atmospheric reactions, transport, and deposition of PFAS to surface and groundwater waters that feed drinking water sources. The second point we hope to have is, or we hope to address and build upon, is there is limited to no information on the atmospheric reactions these PFAS compounds undergo during long-range transport that can influence how well they are deposited. Ultimately, the knowledge gained from this research will benefit stakeholders within North Carolina and beyond. And results from this work, of course, will be presented in peer-reviewed journals, as well as shared with local, state, and federal agencies. Okay. We wouldn't be here without the support of the co-laboratory. It was said before, but we cannot thank the collaboratory enough to herd all of us into the same room and to do something that is really unique. I also acknowledge too funding from North Carolina GA, and also NCDEQ and DAQ for working with us to allow us to have access to one of their sites. And with that, I'd be happy to take any sort of questions that you might have.
All right, thank you. Okay, so I'm recycling a question from
Sure.
a previous speaker's time. How far away from the Fayetteville Works plant are you finding the air contaminated with these PFASs?
Right. So based upon the slide I showed, the PFAS can travel at least this far from the plant. But again, it's highly dependent on where that air mass comes from.
Okay. Okay, this one's, so Grays Creek is around the DuPont Chemours plant, is an agricultural area with corn grown for ethanol to be combined with gasoline for automobiles. Can PFASs be discharged into the air via these gas emissions?
Can you repeat the question?
So I think referring to the,
Combined with gasoline. I'm not sure. Creek around
are they referring to the ethanol
Yeah, I'm not
production?
sure.
As it stands now, basically we'll know more as we collect. We'll know more about the short range as well as the long range transport of PFAS, and I'm not sure if we'll be able to exactly pin it down to land use, but that would be an interesting.
I wrote the question. So the question is, the corn is contaminated from the Grays Creek area.
Okay.
And so we're combining it with gas, and it's going out into the atmosphere via gas emissions.
Okay, fair enough. Yeah. So the
Thank you.
ethanol that we use as a fuel is fermented. That's the process, and I don't think the PFAS would make it through that process, but it would be an interesting thing to look more into. So.
Okay, next question. Are there any studies being done on the atmospheric deposition from incineration of wastewater solids?
Wastewater solids. So we're talking about bio and spraying on fields. Is that?
Or the incineration process itself?
Okay. Yeah. So. Well, yeah, the incineration, I mean, I don't know off the top of my head. If any of my colleagues on Team 4 would chime in, that would be helpful. Yeah, go ahead, Barbara.
It just comes down to the temperature. So if the temperature of
please feel free to follow up with these folks at the reception. It's a great opportunity for
Sure.
a little more interaction. I think I'm going to hold this one. This doesn't appear to be related to your work. So I think we'll stop here and move to the next team. But thank you
Okay.
very much,
Yeah.
Dr. Mead. Okay. Our last team, and certainly not our least, is the Applied Research Opportunities Team, led today by Dr. Jamie DeWitt. Dr. DeWitt is from East Carolina University, and I see not only her name but her face all around the country these days talking about her work. So Dr. DeWitt is an associate professor of pharmacology and toxicology at East Carolina University. Her lab studies how early life exposure to a variety of agents, including environmental contaminants, may impact the immune, nervous, and endocrine systems during development and into adulthood. The research objectives of Team 5 are many and they are complex, but the overall goals of the team is to better understand the impact of PFASs on human health and also on the health of our natural ecosystems, including the Cape Fear River. Thank you, Dr. DeWitt.
Well, this is a very sensitive microphone. So speaking of water, I got a video from a colleague this week. She lives in Arkansas, and it was a video of her neighbor's backyard flooding. It's strange to think that you all are in drought conditions here to the point where you have an irrigation restriction with potential fines coming up in the future if you violate that irrigation restriction. Well, thank you, everybody, for inviting me to be here, and thank you for allowing me to be part of this collaborative effort. It is really a wonderful way to work with colleagues from around the state who I might not have had the opportunity to work with before. That being said, it's also not wonderful that our work is to figure out what these compounds that we're all drinking and breathing and ingesting are doing to our bodies. One of the goals then of Team 5 is to address some of the context associated with all of the data being produced by these other teams. And this is a very complicated team because we have lots of different questions that we're trying to ask. But our main goal is to provide a little bit of context in terms of health effects, where additional sources of PFAS might be, how they get taken up into plants. Now, bear in mind that I am, along with Dr. Fry, the co-team lead of a very diverse team. That means that I'm going to share some information with you about which I know very little. So about 90% of what I'm presenting today, I know very little about the topic. My colleagues have given me some slides. I'm hoping that some who are here might jump in if there are some questions specific to their work. So if you want me to answer a question about immunotox, no problem. If you want me to answer questions about some of the other topics, I may struggle a bit. All right, so that being said, when we think about context, we have to think about some of the concerns that you all have about what's happening to these agents in the environment and in our bodies. And so a lot of our team approach is based on the questions and concerns that you all have about PFAS. We are small independent teams that have tentacles into the other teams. So our level of collaboration among one another isn't as high as the individual team members on some of the other teams, and that's because the questions we're asking are very specific. So keep that in mind as well. One of the questions that we have is, what are some other sources of PFAS into the water that we're drinking? Is a facility that produces these the only source? And Dr. Mort Barlatz from North Carolina State University is asking about these other sources. Specifically, what happens to the trash that we dispose of that contains PFAS? Do these pieces of trash that go to landfills produce PFAS in the leachate or the juice that comes out of landfills? Many of these kinds of water end up going to the same facilities that treat our sewage. And these can be potential sources of PFAS into surface waters that then may end up as biosolids or as sources to our drinking water. And he's asking questions about these types of contaminants, this type of source. And so he has several objectives, and he's asking questions about publicly owned treatment facilities and the leachate water that they receive from landfills. He's also interested in asking questions about construction and demolition landfills because this might contain carpeting or other flooring materials and adhesives that also are sources of PFAS to the environment. And his approach is to look at landfills and the water that comes out of landfills, that juice or leachate. He's also asking questions about what comes into wastewater treatment plants and what leaves wastewater treatment plants. So he can ask about the potential contribution of that leachate water. And then, as I mentioned, he's also going to ask questions about construction and demolition landfills, about which we don't really know much in terms of their PFAS contribution. And his research approach is really based on this mass equals concentration times volume. So one of the things that he'll be doing is measuring the volume of water treated by wastewater treatment facilities, and this is something that's in millions of gallons per day. So he'll be asking about the contribution of leachate water in terms of PFAS, and then adjusting that by the volume or the flow rate of these different treatment facilities. And for some of these, he has to figure out. He's already sampled quite a few landfills and treatment facilities, and so they're looking at what happens over time so that he can ask questions about the flow rate, and then what happens in terms of the concentration being put into and removed from or discharged into the environment from publicly owned treatment facilities. He has some nice figures for us to demonstrate that he's looking at some different volumes or millions of gallons per day. So this reflects how much water is treated by different facilities. And you can see we have some facilities that handle, or very few facilities that handle very large volumes of water, and many facilities that handle relatively low volumes of water. And this is to demonstrate that he'll be looking at different types of facilities and different volumes of water that these facilities handle. And this tells you a little bit about how these facilities are distributed across our state. So he'll be looking at facilities in the West, in the Piedmont, and in the coastal plain. Our next team, and I think Dr. Belcher is here. Are you still here, Dr. Belcher? So you can answer questions? Great. Everybody likes Dr. Belcher's team because it's all about alligators and striped bass. And so he's asking questions about whether or not PFAS are accumulating in wildlife that are important indicator species that might tell us something a little bit about ourselves and what we might take into our bodies. And so he has questions about how these PFAS move into the bodies of wildlife. Can he detect them? Are they going to stay in the bodies of wildlife for a long time? Do these newer PFAS that we're finding in the Cape Fear River accumulate in wildlife? Can he detect them? And then he's asking questions also about the health of these organisms to determine if their health is affected, what are the ramifications of that on our health? And he's also asking questions about concentrations in the fish. If we eat the fish, does that mean the PFAS are going to move into our bodies? In terms of his research approach, he's sampling striped bass from different locations. Part of me always wants to say bass whenever I see the word bass, and so I have to say bass, not bass. And then, of course, when you think of saying the wrong word, you end up saying the wrong word. So if I say striped bass, just go, okay. So anyway, so he's looking at some different locations. So he's looking at sites of known contamination, and then he's also looking at reference or control sites, or sites where he anticipates there to be very low concentration, so he can compare contaminated fish with relatively uncontaminated fish. He's also doing the same with alligators. He's got some sampling